It looks like we're just about there. Welcome back, everyone. It's official. We're now on week 7. So congratulations getting this far, folks. Class attendance definitely has thinned out over the weeks, but I'm happy that you folks have made it in today. For the announcements today, our quiz number 5 is going to be due on Thursday of this week. And the bigger announcement is that our upcoming exam 2 is in 2 weeks from today. So that means we're going to really just repeat the same pattern that you saw going into exam 1. On Friday at the end of this week, probably at the very start on Friday, this is going to be one of the first things I do, even before grading quiz 5. I'll start writing down the exam 2 information. That way you'll know the exact coverage of what's going to be on the second exam. And then I'll start including the review problems, just like we did on exam 1. And in addition to posting a review exam on the Newton homework system as well for folks that might have felt that was a good way to review. So we're going to pretty much just repeat the cycle for how we got into exam 1. On Monday early this week right here on midterm week, I'll be contacting every student in the class individually. I'll be using the Canvas system. So I'm going to go here to write out a message to each one of you on how to schedule your upcoming exam 2. But really, it's going to be just the same as how the exam 1 was done. Any questions at the moment with any of those announcements? Okay, well, welcome back, folks. We're going to start continuing on through section 6.3 on factoring more and more different kinds of polynomials. Section 6.2, we are factoring trinomials. These are polynomials with just 3 different terms. We looked into the trial and error method, as well as the AC method. And here we're going to factor special products, but in a certain sense, this is kind of a fun section. I think factoring is sometimes a little bit tough in section 6.2 until you get the hang of it. Section 6.3 has very little to no trial and error whatsoever. But the difference is, the trade-off is, we're exchanging all the trial and error in the formula, in the factoring, for using certain formulas to factor. So here's what the problems are going to start to look like. Instructions will say to factor completely, but for every one of these problems, there's going to be some kind of formula that's in the background that's going to assist us with the factoring. First, we're going to be looking into the perfect square trinomials. What we mean by perfect squares are, well, just like the numbers. For example, in ordinary integers, the perfect squares would be 2 squared for a 4. Not sure why I skipped 1. 1 squared would be a 1. 3 squared would be a 9. 4 squared would be a 16. And so on. These are all the perfect squares. Let's keep on increasing this list. We should see a good set of them. 5 squared would be 25. 6 squared would be 36. This is actually useful in this section. So just for a warm-up, let's write out even more perfect squares. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. And this is where it starts to get a little bit vague, foggy. You might reach for a calculator at this point. 12 squared is 144. 13 squared is 169. And this is the point at which I'd personally tap out and say, see the calculator. But these are the perfect square integers. And what we're doing is extending this concept into perfect square polynomials, these kinds of things here. What makes it a perfect square is we're just taking something to a power 2, just like we did on this entire list here. We're raising things to power 2. to get the perfect square and seeing how it expands out. But the trouble with this is we're not going to FOIL out a plus b squared. This is essentially going to be the answer. This is what it means to factor, try to get to this point. We're going to start with things that look like this. If it fits the pattern, then it immediately factors into that format. And the way you could check each one of these is as follows. Take a minus b squared. This could be rewritten as a minus b times a minus b. We were to FOIL out this expression, we would first take a times a for a squared. Then we would take the a times the negative b, so minus ab. Then we'd start to distribute b into the group. It'd be minus ba, but we can change that to a minus ab as well. Then multiplying negative b times negative b would be a positive b squared. The inner two terms right here would combine, and we would have a squared minus 2ab plus b squared, which is the format of this formula right here. So anything of this form can be immediately factored down to a minus b squared. And likewise, in this format, this factors down to a plus b squared. I believe the only thing different between both versions is the sign that's in the middle here and here. So that's how the formula goes. It's one thing to understand the formula and a whole new thing to put it into practice. And so that's what we're going to be doing on these problems down here. Any questions first with the formula itself? Okay, well, to factor each one of these, first thing I would observe is trial and error is still a pretty good call on these kind of problems. Even though there's a formula in the background, the trial and error method from the very last section would first say, you could rewrite this as something times something in this format. Positive sign here means signs are the same. Positive sign here says both signs have to be positive. Then to split up x squared, we can go x and x. And now we just need a choice for what should go here and what should go here. But sometimes finding the 25 is almost a dead giveaway to these problems. It isn't guaranteed to be a perfect square trinomial, but it strongly suggests give it a try. In other words, if 25 appears as a perfect square, one natural way to factor 25 would just be 5 times 5. So let's put a 5 here, a 5 there, and see if it works out. The check in the problem is just to multiply from here to here. That'd be 5x. Then multiply the inner things here to here, 5x, just like we did in the last section. When we add those two together, we get 10x, which is the middle term that we were going for. It tells us that this is the complete factorization, and we could take this even one step further. X plus 5 times itself, if we use exponent notation, is just x plus 5 to the power of 2. All this is indicating is repeated multiplication, just like we saw here. That's why it's written in this format. We had something of the form a squared plus 2ab plus b squared, and we factored it down as a plus b to power 2 in that format. That's our first one down. Any questions, folks, on getting through that first example? Okay, so pretty much these are still very similar problems like in the section 6.2. We're still taking the same kind of first initial steps, analyzing the signs, placing down values using trial and error. It's just that if we notice that there is something special, like the perfect square integer here, or the perfect square coefficient and integer here on that term, then it strongly suggests the problem is going to end in this kind of way, that there really was no trial and error, but we just have to spot it through pattern recognition. For example, this very first term can be split up as 10c times 10c. So that makes up the 100c squared. This term right here, 49, that's our perfect square over here, just like 100 was. So the natural way to split this one up would be 7 times 7. Actually, I like it going down below just to match what we did on the last one. So if this one factors, the very first thing we should try is to write it out as this. The leading terms should be 10c, 10c. The last terms should be a 7 and a 7 to make up that 49. Positive here says both signs are the same. And negative here says they both have to now be negative signs. So if this factors, should be our first thing to try. 10c minus 7 times 10c minus 7. We should still check this out because it's not guaranteed to work. We need to see if we get to the negative 140c. But if you multiply here to here, this is just half the check foiling it out entirely. That much is going to be negative 70c. Multiply here to here, that's negative 70c again. We tally these up. Together, negative 70c minus 70c is negative 140c. So it tells us we hit that middle term and the check is complete right at that stage. So just like on the last problem, the whole thing can now be rewritten as 10c minus 7 to the power 2. And that's how the problem ends once again on that one there. So really fast on the last problems, sometimes the trial error did take a little bit of time to come up with the right values.
Can you make the equation can you make the like equation bullets a bit bigger, please?
Yeah, do you mean just the zooming in, say like this? Or did you mean at the very top up here?
Oh no, that's good.
Right about this zoom right here?
Mm-hmm.
Yeah, you bet, I can definitely do that. So this is what it would factor down like that. Yeah, sometimes in different screens, it could be pretty hard to read. So like if you're on a cell phone, it'd be almost impossible. But even on a normal computer screen, like on a laptop, sometimes it needs to be zoomed in to see entirely. So thanks for mentioning that, Clay. Well, we'll try this out again on the very next problem down below. A little bit more going on with this one. But one thing to observe about part C is all the terms here are even. That means we can factor something out. 2 factors out of everything at least. Now, if we factor out a 2 on this one, it would leave behind 81, which is a perfect square. Also, all terms have a factor of x and a factor of y. So the idea on this problem on part C is first, factor out the greatest common factor. So the greatest common factor would involve 2 because it divides all the terms. X is common to all the terms, but the smallest power of x is x power 1. Similarly for the power y right here. So we can factor out 2xy. That means we're dividing 2xy into all 3 terms. And this is going to leave us a 4 x squared on the very first term. Divide out the 2 on the 72 and we'll get a minus 36. The power of the x and the power of y reduced by 1 because the x and y are dividing into it. So it's just a negative 36xy. And here, when we factor out xy, this xy's vanish, and we're just dividing this part by 2. So this is going to be a plus 81. At this stage, this is what we would be left with, 4x squared minus 36xy plus 81. We factored it out a little bit, but the instructions say to factor completely. So we need to see how much this can reduce on the inside. Any questions to this stage so far? Okay, so on the next step, we can rewrite this as 2xy. Put down a pair of parentheses using the trial and error method. And 4 is a perfect square. So best way to split it 4x squared as an initial.
Are the exponents 2s or 7s?
The exponents are 2s right here. So this is a 2 and this is a 2. Yeah, so that's why it came down to a power 1 here and here when we factored out the xy on this one. Other questions at the moment? Okay, then factoring out this 4x squared, we can go with a 2x and a 2x to start us off. For the 81, 9 times 9 makes 81, so we should try a 9 and a 9 on that one. And same issue with the signs as in the last problem. Positive here says both signs are the same. The negative here would say both sides have to be minuses. So minuses would go there and there. Last thing we have to do is to see if we really get to negative 36xy. Well, multiplying here to here is, oh, we wouldn't get to negative 36xy. There's still something missing on this. Let me double check. I had an xy here. Let me see, one little thing that I might have as an issue on this problem. I had 4x squared. Factor out an xy here, leaving an xy. I think I have a typo in this problem. Actually, this problem is written, looks like it was stopped right at that spot. Because if I have an xy here and nothing involving y's, it looks like it would just end right there. Oh, geez, this one is a little bit trickier than I thought just on initial glance. Sorry for the confusion on this one. You know, probably what I was thinking on this problem was a y power 1 right here. That would change this entire problem, making it go the way I thought it would. But for this problem, this would be factored completely right at this step. So this is completely factored. But it looks like it's not quite the problem I intended, so let's do a second version of this one. I'm going to call this part number C, part 2. This is what I think I intended I should have had in this problem when I initially wrote it. I think I meant for this just to be a y altogether, which changes how this whole thing is going to go. So let's try it out this way. I think this is a better version of what you might see as a real homework exercise. This one was a little bit wonky because of the xy here. There's no way to factor it any further. So let's try this out again in this format. We'd first still factor out the greatest common factor, 2xy, which means we're dividing 2xy in each one of these three terms. Here, that's going to leave us a 4x squared. Now, this is the change I made in red. Factoring out the xy on this one is going to leave us a negative 36. But just an x on this one, making the problem now suddenly doable. Factoring out 2xy here means just dividing 2xy, leaving us a plus 81. And now this problem would read 2xy multiplying two groups. That's where we aborted the problem right here, noticing the issue. But this time you can split it as a 2x, 2x. 81 can split as a 9 and a 9. We can go minus on both. And this time we get the right thing, because if we multiply here to here, we get negative 18x. Multiply here to here, it's negative 18x again. That's what we did on the prior problem, but we were never going to get an x and a y. That y was stopping factoring from proceeding. But these two this time would add up to negative 36x. There's no y there to stop the factoring. And so this problem can proceed as in the normal way. This would just turn into 2xy times 2x minus 9 to power 2. So that one would have been the doable version. Well, part C was a weird one where we could only factor out the greatest common factor. You know, that sometimes does happen in the homework. Sometimes there's problems where that's the only thing that you can do. That'll happen in section 6.4 in particular. But I think this is a more common actual 6.3 problem. So sorry for the quick edit on this problem to make it more of a doable one. Well, that's factoring perfect square polynomials so far. Next group we're going to look into are the so-called difference of squares. But any questions getting through this one so far? Okay, so here's the next set of formulas. And really, these are, I'd say, my favorite formula when it comes to factoring. The difference of squares pattern, as it's said in the notes, is something that actually comes up a lot in algebra, whether you're taking intermediate algebra, pre-calculus 1, pre-calculus 2, calculus. This just seems to come up very, very often. It tells us if we have a squared minus b squared, that's an automatic factoring as a plus b times a minus b. This is one we don't even need to check. This is just guaranteed to work. And it comes with another warning. The difference of squares pattern, a squared minus b squared, automatically factors in the correct way, but the sum of squares does not. If you're using ordinary real numbers, a squared plus b squared is non-factorable, which is a pretty weird fact. We'll look into that on the examples down below for some similar problems. So one way to think about why this formula would be correct is we try to FOIL out a plus b times a minus b. First, you would just take a times a for an a squared. Then we would take a times negative b, so minus ab. Then we would take b times a, and that's going to be positive. Either ba or a times b would be equivalent ways to write it. Then finally, b times b would come out as positive b squared. And notice the terms in the middle, they just cancel immediately. So it turns into a squared minus b squared. This is kind of a check to show the formula is correct. But our goal when we're factoring is to go from the left end to the right end. And also, whenever this comes up, we just have to say not factorable. And it'll come up quite a bit in these notes here, as well as the next note, section 6.4. It's kind of a similar kind of problem. It does involve squares, just like the perfect square problems we were just looking at right above right here, where the 4 was 2 times 2 and the 81 was 9 times 9. The only difference is there's a minus in the middle, and we're only looking at 2 terms. So the 2 terms is sometimes a giveaway that we're possibly using the difference of squares pattern or formula, you could say. Here's how it would go. If it's x squared minus 9, this is kind of one of the all-time nicest factoring problems ever because you first factor x squared, that's just x times x. A negative sign right here automatically says the signs have to be different. They have to be positive and negative on this problem. The 9 is a perfect square, which factors as 3 times 3. So that's the first thing to try. Go plus 3 and minus 3. And in fact, that's now guaranteed to be the answer. On all the prior problems, we were FOILing out the inner
Why is
term.
9 a crooked square?
9 is a perfect square because 9 can be rewritten as 3 times 3. Or in other words...
Oh no, sorry. I thought you said it was a crooked.
Oh, sorry, that was my bad there. Yeah, 9 is a perfect square rather than that. Yeah, I misspoke there. Other questions at the moment? Okay, well, that's pretty much how all of these go. X squared minus 9, that was just kind of like the warm-up problem. The numbers can get bigger, but if they're perfect squares, the same idea applies. You know, first thing you'd want to check though is there a greatest common factor? On this one, 81, only 3's divide this, 3, 9, 27. 64, only powers of 2, so it doesn't seem to have a perfect square, or excuse me, a greatest common factor. But even better, 81 is 9 times 9. 64 is 8 times 8. So if we have perfect squares, then the difference of squares pattern should hold for us. And that means we can just rewrite this whole thing as 2 sets of parentheses like before. Let me get that little mark off there. So 81 just split up as 9 times 9. Negative sign in the middle always means the signs have to alternate as plus and minus. And for 64x squared, we could just break this up as 8x and 8x. And then that completely resolves the problem. Again, we don't even have to check these out by FOILing. It wouldn't hurt if we did. If we FOILed this out, it'd be 9 plus 8x times 9 minus 8x. That sign change is the key thing about it. 9 times 9 here would give us the 81. 9 times -8 would give us -72x. Then the other half of our check, we would multiply here to here, giving us positive 72x. Here to here, that's going to be -64x squared when we multiply those together. So the reason the check works is the -72x and the positive 72x automatically cancel. And that's the effect of alternating the signs from positive to negative. So that tells us this problem is immediately done. Again, they go really, really fast once we see what the pattern is. Any questions on getting through part B? Okay, here's where it gets a little bit more challenging on part C. On this one, doesn't look like it's a perfect square at all, just because the power on x is 3 and same on the power of y. But we have xy on the first term, x and y on the second term, meaning we can just factor that out. And while we're at it, we should just take out the greatest common factor. So this is like part C on the prior problem above on the notes. If you notice the greatest common factor is in the problem, then that should be our first step. So let's say here, first, factor out the greatest common factor. So once we do that, the problem should be a little bit more easier to get through. Between 90 and 160, looks like we could factor out a 10. When it goes between base x, the x cubed and the x, we always go for the lowest power. So x factors out. And likewise, between y cubed and y power 5, lowest power that factors out would be y cubed. Then we're dividing 10x y cubed into both terms. Divide by 10 here, and it just leaves a 9, but that's a perfect square, so that's helpful. Divide by x drops a power by 1, so it's 9x squared. And y cubed just cancels completely when we divide it out. Then we do the same thing over here. Divide this by 10. It's going to be -16. X divided into this x is a cancellation. And y cubed into y power 5, that would just leave a y squared. And again, that's our exponent laws working really well for us, giving us that y squared on this one. So now it's 9x squared minus 16y squared. It's yet again another difference of squares, so we can factor even further at this point. 9x squared is just 3x times 3x. So the first term is a perfect squared. And likewise, 16y squared is just a 4y times 4y. So using this information, we can solve the rest of the problem. Any questions getting through that first step? Okay, here's how the rest of it goes. 10x y cubed just has to copy down. The rest of the problem was going to be 2 sets of parentheses going like this. 9x squared, we can split up as 3x. 3x. Negative sign here means we have to go plus and minus. There's no other choices. 16y squared will go 4y. 4y. And because this is a difference of squares, that's just automatically the answer right at that exact step. So we did it, folks. That's 3 difference of squares problems. They're kind of nice in a certain sense because they go fast once we recognize the pattern. And they're even nicer because you might do a check. But unlike the last problems, the check isn't strictly required. These are guaranteed to always work out. Every time you spot a difference of squares, this is the automatic way and only way it could factor. Well, any questions on any one of those 3? Okay, so this is how difference of squares go. And that takes us to the warning. If you see a sum of squares, then that's just the indication to stop, say not factorable, because there's nothing we can do with it. Sum of squares mean there's a plus in the middle. So all 3 of these problems were doable only because of the minuses in the middle of these terms. So the moment we get to 9 squared plus 25, there's nothing we can do. This one is just automatically not factorable. That's kind of weird. We just stop right at that stage. We don't even attempt to factor it. You know what makes this kind of an interesting problem is seeing what happens if you do try to factor it. So I'm going to box this out just to convey that's the total answer to this one. Let's attempt to factor it just to see what would happen if we give it a try. So take 9y squared plus 25. If this is going to factor, it's going to be in this kind of format. And we can try just about anything we'd like. For the 9y squared, we can go a 3y and a 3y. That makes sense because 3y times 3y, if we FOIL this out, gives the 9y squared. For the 25 here, we would go a 5 and a 5. And now for a positive sign here, we have to determine what the sign should be. Positive here means the signs have to be the same. So we could try a plus and a plus, but now if we were to FOIL out this answer, the first two terms would multiply to give us the 9y squared. The last two terms would multiply to give us a 25. But you know what doesn't happen is the middle terms, they'll never cancel. When you multiply here to here, you get 15y. Here to here is 15y again. And that gives you a term in the middle, 30y. There was no 30y here, and so that tells us this factoring does not work. Put an X there to say this failed on that try. You could try putting in minuses here and here, but then you get the different problem. If you put in negative signs, that would be negative 15y again, and there's no middle term of negative 30y. So it says if no matter what you try here, it always fails. The problem is we're only using real numbers, and so the full statement is this is not factorable using real numbers. Using other kinds of numbers, sometimes called imaginary numbers, textbooks these days often call it complex numbers, you can make it work, but that's going to be later on in our textbook. So these ones, whenever we spot them, we'll just say not factorable. They're kind of a nice one because once you recognize the pattern, that it's a plus in the middle with squares, then it's a freebie problem. That's always going to be the end answer. Any questions on that one there? Okay, so we have sum of squares that never factors. We have difference of squares that always factors. And here's where it gets really interesting. We also have a pattern for sums and differences of cubes. It turns out it's the sum of squares that has a problem. A squared plus b squared just never factors. But as a sum of cubes, it definitely will. This is the pattern of which it factors. A cubed plus b cubed will always factor as a plus b times a squared minus a times b plus b squared. And likewise, a cubed minus b cubed factors in this related pattern. This is kind of weird, so we should justify it by multiplying just to show how the formula works. Then we'll try it out with some examples down below. First though, this is going to be content that could possibly be on exam 2. And the math department has a policy for exams in this class. This being a coordinated class means they make some of the decisions on the exams. They don't allow me to put formulas on these exams, and so we do have to memorize these formulas here. The trick to memorizing it is if you memorize this one, then there's a small weight change you make to get to the second one. So the idea is the only differences go here. If it's a cubed plus b cubed, you put a plus here on the very first factor, and then you go minus. So that's one formula down, and you can get the second formula by just swapping all these signs you see highlighted in yellow. Change plus to minus, change plus to minus here, change minus to positive here, and those are the key differences. So memorizing one can give you the other with this mnemonic, just changing those three signs. Still doesn't explain how it works, so we'll FOIL out to one of these just to show how the pattern goes. Any questions first about the formula itself? Okay, let's check out this one right here. The check on this one would go very, very similarly. I think this one's kind of surprising because that negative just seems a little bit weird. So if we go a plus b times a squared minus ab plus b squared, it's still a FOIL problem, even though the FOIL acronym kind of fails because there's three terms here. But what doesn't fail is the pattern. We still multiply in the same kind of way. We take the first term right here and we distribute through, multiply there to there. A times a squared is a cubed. Multiply here to here, a times negative ab is minus a squared b. And then last, multiply here to here. This will be plus a squared, a b squared, plus a b squared. You have to say the powers right, or else it's confusing. Then you start over and distribute b through. B times a squared. Well, you know what? We had that before. We could rewrite that as plus a squared times b. We can change the order of multiplication. And I'm putting it over here just because those are like terms and they're going to cancel. Then here to here, that's minus a times b squared. And then finally, multiplying way out here, b times b squared is plus b cubed. That negative sign was pivotal because it arranged for these to just cancel out, these set of terms to cancel out entirely. All we're left with is just a cubed plus way over here, after all the cancellations, b cubed. Again, same idea if you multiplied out this formula. So that's how the formula works. It's a proof that it's the correct formula. But again, we're working the formula going from the left to the right. So that's what we're going to practice on the next two problems down below, just using those formulas. In fact, we'll practice it again in the next section, 6.4, which is just an overall review section now on factoring. Well, first, any questions on either two formulas before we try them out? Okay, the trick to getting this formula to work out is, if you can say what the A is and the B is, then you'll know what A squared is, AB is, and B squared is. You just have to make sure you put that negative there. It's a tricky kind of pattern because there's lots going on with this formula. But the fundamental thing is it deals with cubes, things raised to a third power. So if I can make this look like something raised to a third power, then we'll be able to start the problem. I'd say this is a good step to try to start using the calculator and just looking at what the perfect cubes are. Sometimes these are pretty large numbers. Perfect cubes rise really fast in size. They all look like this. The first one is 2 to the power 3. The next one is going to be 3 to the power 3, 27. We haven't hit 64 yet, but if we go 4 to the power 3, 4 times 4 times 4, we get the 64. So having a calculator nearby is pretty helpful for these kind of problems. It tells us the 64 is just 4 raised to power 3. And x is definitely x raised to power 3. We're just looking at it right there. So this is how I would start off this problem. I would rewrite this as something to the power 3 plus something to the power 3 because I'm thinking of this formula here. What makes this work out is nothing special on that first term. That's just a different way to write down x cubed. But 64 can be rewritten as 4 to power 3. And now this tells us what a is and what b is. We'll just drop the a and the b in those positions. Then we have to throw in an a squared here and a times a b there and a b squared there. So this is what it's going to look like once we identify A and B. Let's do this, just that. A in this problem is just X. We also need A squared, so immediately I probably write down A squared is X squared in this problem. So that's the A in the problem, and likewise, B in this problem is 4. So if B is 4, we can say B squared. That's just 4 squared for a 16. And the last thing we need is A times B, the middle term. So A times B in this problem, that's just going to be 4 times X. So we get 4X. So that's going to tell us where everything goes. But since this problem is so well organized just by using the formula, the very next thing I would do after getting the A and the B out, writing these things down, is just rewriting the formula, because that's going to tell you where every little piece is going to fall in. It's also going to just help you memorize the formula at the same time. So this is going to be A plus B times A squared minus AB plus B squared. So these are the A parts of the problem. This is the B portions of the problem. And this is how it factors in one, well, not exactly one step, in several steps. But from here to here, from the formula down, this is the last step. Just throw in what the A is in this problem. It's X. So this goes X plus 4. So really, X cubed plus 4 cubed drops down as X plus 4, just like it did from here to here in the formula. Then we put in the value for A squared. That was the X squared from over here. Minus A times B, we calculate that to be 4X. Plus B squared. On the right, we show that B squared is 16. And at this stage, the problem is totally done. The other thing that's a cool feature about these problems is these are not factorable, which is a kind of a nice surprise. And it's also helpful because it tells you every time you use the sum and difference formula, your step ends right here. It can't proceed any further from this step on. But we did it, folks. That's using the sum of cubes. We'll try the difference of cubes on the next problem. Any questions first, getting through this one? Okay, here's how the next one goes then. Let's do it kind of the same kind of pattern that we did on the last problem. 125, we bring out our handy calculator. 4 cubed goes 64. The 5 cubed comes out as the 125. And we recall that 3 to the power of 3 gave us the 27 as well that we see in this problem. So we can start just by putting in the same kind of organization. 125 minus 27b cubed can be brought down to something cubed minus something cubed. 5 will go in here for the first part. So that's going to be the A in the problem. And 27b cubed, we can put in as a 3v. So that's going to be the B part when we go to the B portion of the formula. This works because if we raise something to a power 3, the 3 gets raised to power 3, so it's 27. And this 3 also affects V, so this becomes a V cubed as well. Once we get down to here, we're also going to need a formula. We probably also want to complete these things on the right. It's not required, but sometimes it's just helpful for organizing what goes into the formula. So the formula is not this one, but like we mentioned before, it's rather close. We just make 2 changes. This switches to minus, that switches to plus, and that gives us the entire formula. So let's go rewriting that formula as A plus B or excuse me, a minus b, that didn't do what I said we were going to do, that switches to minus, so let's actually switch it. A minus b times, here that portion switches to plus. So a squared plus a times b plus b squared. And these are the only two differences from the formula we used in part A and formula in part B. In other words, we're just making that a minus and plus like we saw above here on the notes. So like we said, if you memorized one, you have the other. We just have to know exactly what A is so we can get a squared and a times b. We also need to know what b is so we can get the rest of the formula as well. The moment we wrote this, it told us in the formula, a is 5. So then a squared is 5 squared for 25. Then rinse and repeat. The moment we wrote down 3b cubed, it told us b is 3b. So if we square that, b squared, this is our exponent laws now working for us once again. 3b squared means you squared the 3 first to get a 9. Square b to get a b squared. And probably the easiest mistake to make in the homework is to accidentally call this a 3b squared, forgetting to square out the 3 to get the 9. And then last, a times b is going to be equal to 5 times 3b. But that altogether is just going to be 15b. So that's our term in the very middle. So now we have all 5 parts. There's lots to plug in here. That's why the organization on the right is sometimes really helpful. But once we plug it all in, our work is done. So we'll go 5 minus 3b. I think we mentioned this comment many times already in this course. Much of algebra is just a whole lot of substitutions. And that's exactly what we're doing. We're substituting in what we said A is, what we said B is. Next, substitute in the value for a squared. It was a 25 in this problem. We even calculated a times b, so substitute in 15b for that. And we calculated b squared, so substitute in that b squared is 9b squared. Then this is exactly where the problem would end, right at that step there. Well, we got it, folks. That's the factorization of the difference of cubes, 125 minus 27b cubed. Any questions at all doing either one of those? Okay, well, that's so far been the rundown of all of the factoring techniques so far that we've got in the course. What we're going to be using these for is solving equations by factoring first and setting factors to 0. But the good news is, before we just jump into equation solving, the very next section is a review section of 6.2 and 6.3. So we'll take a look into that content very next. So now off to the next section. Section 6.4 is the general strategy for factoring polynomials. And here it's just going to be some random polynomials. So we're going from things are kind of out of context. Both of these involve 2 terms, but the way we factor them are different. This one's 2 terms, so this factor is different still. And several others that we're going to try to find out what the right strategy is. So every one of these is kind of scrambled from the order that we've been going through this section in chapter 6. It's our job to determine what to do on every one of them and see what the right strategy is for factoring. By the way, this one looks pretty rough. The huge number is 686, x to a power 4, but over here is x to the power 1. Also, it looks like 2 divides both of those. So the first strategy we're going to use is really the most fundamental one. On every single problem, step 1, factor out the greatest common factor if possible. If there's a common factor other than 1, then that's the thing that we should do at the very, very first step. So let's give that a try on this one. 2 divides and x divides. So it looks like the greatest common factor on this one is just 2x. Divide 2 here and we get 343. Factoring out x just drops the power by 1, so this is x cubed, plus divide this by 2 and it's 125. X cancels out and it just leaves y to the power 12. At this stage, however, just based on the very last section we were looking into, and the fact that we have 125, we know that's 5 times 5 times 5. Let's pull up that calculator. Here it is, 5 cubed. Let me bring those kind of closer to each other. 343 looks suspicious, but at the moment, this looks like it is a sum of cubes. So step 1 was to take out the greatest common factor. Next, factor as a sum of cubes on this one. The 343, though, is kind of mysterious. Let's make sure that really is a perfect cube. We've looked into 5 cubed to get 125. We go into 6 cubed, that's 216, so still not 343. 7 cubed, that hit it perfectly. 7 times 7 times 7 is 343. So that tells us it really is a sum of cubes. So let's rewrite this again. This whole thing can now be expressed as 2x multiplying, let's go with a bracket on this, multiplying something to the power 3 plus something else to the power 3. So what goes here, let's take a look at our calculator again, is 343 is 7. If we put x there, raise this whole thing to the power 3, we get 343x cubed. So that's a start. That tells us what the a coefficient is going to turn into. And likewise, 125 we can drop down as a 5. We just need a power on y, so that when we raise the whole thing to power 3, we get a power 12 out. Anyone happen to see a good power to throw here for y? Yeah, good call, Tracy. This one has to be power 4, exactly. So put power 4 here, and we're in business. The check on this is you can rewrite 5y to power 4 to the third power by just using exponent laws. This turns into 5 cubed plus, or not plus, excuse me, times y to the power of, in this configuration, the exponents multiply. So that's 3 times 4, getting us back to the power 12 that we're expecting. But that means we have our b coefficient down. Next thing to do is write down the formula, and then we can fully expand this out as the final factoring. So 2x is just coming along for the ride. This isn't part of the major thing we're trying to do. We can drop the brackets at this stage because what's inside is going to convert into two things multiplied in this kind of way. And the pattern for sum of cubes goes like this. If you see a plus there, a plus goes here, and it'll be an a plus b in that order. Then here will go a squared. From this sign, we alternate it to a minus a times b. Alternate again, so it's plus b squared. So this is the a value we found as a 7x. Then we'll do an a squared. This is the b value, which is 5y power 4. And then we'll do a b squared as well. So just to write down that pattern, in the same way we did it before, we've identified that a itself is 7x, so a squared. That's squaring both the 7 and the x is 49x squared. At the same time, we've identified that the b in this problem is 5y power 4. So this means b squared. We have to go pretty carefully on this one as well because it's a bona fide exponent law. This is 5y to the power 4 squared. In this lineup, you would square the 5 for a 25. Y power 4 squared means exponents multiply, and this would be y to the power 8 on this one. So that's all the portions except for a times b. We might as well multiply that out. A times b is going to be 7x, 5y to the power 4. When we multiply these together, this is just going to turn into 35 x y to the power 4. So that's the a part, that's the b part. Now we have everything we need. There's 5 different things to substitute in. But once we do all those substitutions, the problem is over at this stage. Really what made this problem hard, in my opinion, is without taking out the 2x, the greatest common factor, which is the overall step 1 to all of these problems, I'm not sure what I would do with this. This looks really mysterious as it stands. Taking out the 2x doesn't make the problem easier, or excuse me, doesn't make the problem instant to solve, but it does make it easier because now we have a formula for doing the rest of it. Here's the formula that we copied down. 2x again, just coming along for the ride, and we're just dropping in our values. Look to the right for all the substitutions. A is 7x plus b, which is 5y power 4. A squared, on the far right, it was 49x squared. Minus a times b, we found is 35 xy power 4. And b squared, way over here, is 25 y to the power of 8. So this problem was meant to be pretty challenging. Again, it's a general review section. And so some of the problems go a little bit harder. Some of them are a little bit easier. This one's on the harder end. They're kind of mixed in difficulty. Any questions whatsoever, folks, on getting through this one? Okay, well, let's try it all over again. We have another gnarly looking polynomial, 2 terms again, but a lot of different things can happen with just 2 terms. Notice that 50 does divide 200, and x cubed would divide into x power 4. So minding the step 1, look for greatest common factors, we could rewrite this as factor out 50, x to the power of 3. 50 would go in here 4 times. X power 4 divided by x cubed leaves us just an x. So 4x is our first term. Minus, well, if we factor out 50 x power 3, we're dividing it here. That would just leave a minus 1. And this problem, especially with how part A was, is miraculous. It's done immediately at that step. 4x minus 1, that's a linear thing because it's to degree 1 on x. So there's nothing further to do on this one. Sometimes that's how the problems go. All you did is factor out the greatest common factor and nothing else can happen. That happened on 6.3, but we had to make a second part on that one because that wasn't the intention on that one, it turned out. But it's nice when these happen. That this one's kind of like a little bit of a cognitive break compared to part A. And then we'll see what's going on with the next one. 2 terms again. So again, anything can happen with this one. But this one's a little bit different. That's a perfect square, that power h right there. This one wasn't a perfect square because 200 is not a perfect square itself. 1 is also a perfect square, so we can possibly tackle this one as the difference of squares pattern or formula. So difference of squares goes anything that's a perfect square minus another perfect square can be factored in this way. A squared minus b squared becomes a plus b times a minus b. And that actually works on this one because u power 8, well, that's just u power 4 times u power 4. It is a perfect square. So we can rewrite this as, thinking in terms of trial and error, go u power 4, alternate the signs to plus and a minus, and the 1 is also a perfect square. 1 equals 1 times 1. So we can put a 1 here and a 1 here, and that works. That's matching the difference of squares formula. So that's kind of nice in a way. This part here is a sum of squares. And the reminder for sum of squares is that means that part, the very first factor right here, it's non-factorable. Let me see if I can put in some additional space there. There we go. However, this one, u power 4 minus 1, this is a difference of squares again. That means we can factor u power 4 minus 1 again. So this turns into u power 4 plus 1. Now we're factoring this portion. Following that trial and error, we'd set down 2 parentheses. U to the 4th power can split as u squared times u squared in this kind of way. Signs alternate as plus and minus. 1 continues to be a perfect square, so we'll plug a 1 here and here. And now it's factored even more. The first two terms, or excuse me, the first two factors, the things separated by the parentheses and multiplying, are sum of squares, so we can't factor any of these. But that one's a difference of squares again, and so when the instructions say factor completely, what it means is we'll continue to factor these as much as feasibly possible. If more and more formulas come up, then we'll continue to take them down. Let me fix that to a u. So using the difference of squares formula one more time, first copying up to this stage, we have u power 4 plus 1, u power 2 plus 1. Then up to this stage, this is a difference of squares, so 2 sets of parentheses, where it goes u times u, plus 1 and minus 1. And then finally, mercifully, right at this stage, the factoring stops. It's because the powers are 1 here and here. There's no greatest common factors, so there's nothing further to do. It stops just like how this prior problem stopped right when we got the 4x minus 1. But this one is just a reminder. Sometimes using these factoring formulas can be like an adventure where you use the formulas repeatedly over and over until you get down to this fully factored form like we see down below. Any questions at all, folks, surviving that one? Okay, I've got a couple more review problems for us to take a look into. So here's what's going on with the next one. 8p squared plus 14p minus 15. Well, this one doesn't have any nice tricks. It's 3 terms, so if we're going to factor it, the end answer is going to look like this. 8 is not a perfect square, and neither is 15. And the greatest common factor is, well, 1, but that doesn't help us at all. That's because 2 divides this, 4 divides, but neither 2 nor 4 divide the constant term on the end right here. So it looks like the factoring for this one is going to be either use the AC method or the trial and error method. Let's try the trial and error method and see how we feel about that. So doing this one by trial and error, first thing I would want to resolve is, what should the signs be? A negative right there tells us automatically the signs alternate. It's going to be either a plus or a minus, or we might have to swap them and go minus and plus. It's a good idea to just put down something, and usually you can tell immediately when you have the answer, and you just need a simple sign swap. Next thing to do is to split up 8p squared. And there's several options. You could go 8p times p, that definitely works. But that gives the number 8 a lot of leverage. I would only go this route with the 8p if the number in the middle was really large relative to the others, like maybe 72, 103, something big like that. Usually if the number is about the same size as all the others, you want to kind of split this up in a nicer way. 8p squared could be rewritten as 4p times 2p. It kind of balances out the size of the factors here. And usually that's a good first initial guess for trial and error. So I'll try out to 4p and a 2p. It's not guaranteed to work, but that would be my first initial guess. Then we have to factor out 15. I'm going to just say 15 instead of negative 15, because the fact it's going to be negative is already captured with these two signs we put down. Lots of ways to factor 15. Well, not lots, but two big ways would be 15 times 1 or 5 times 3. But now the order actually does matter here, because when we go to FOIL this out, we're going to be multiplying something here to here and something here to here. One gets multiplied by 4, one gets multiplied by 2. So whether the 5 comes first here or the 3 comes first in here does matter. There's actually 4 possibilities on these. So just to convey that, let's rewrite this as 15 is also 1 times 15, and 15 is also 3 times 5. 4 possibilities, and we can exhaustively look through each one until we find a winning combination. But we're also trying to hit 14p. These two arrows are the things that are going to hopefully add up to 14p. So we might think, instead of trying everything, let's see what gets us there fast. Well, we might put in a 5 here, because 5 times 4 gives us the 20. And then we could put a 3 here, because 3 times 2 gives us a 6. And the difference of 6 and 20 would be 14. But notice we're not quite there, because 4p times negative 5 is actually negative 20p. 3 times 2p is actually positive 6p. 6p minus 20p is negative 14p. So we are so close, but not quite on the target we want. But here's the next concept. If you hit 14, you basically got it. Let's solidify the 3 and the 5. They're right. The thing we really need to change is the signs in the middle. Let's swap that positive to a negative. And the positive over here, or excuse me, the negative over here to a positive. Doing that, now the inner product is negative 3 times 2p, so negative 6p. The outer part, when we FOIL it, is a positive 20p. And 20 minus 6p gives us positive 14p. That nails the middle term, which tells us the trial and error is over. This is the one and only way we can factor 8p squared plus 14p minus 15. So the trial and error method can be a beast sometimes, but it turns out this is the option that got us there. Once we went with the factoring of 8p squared, 4p times 2p. It also can be kind of nerve-wracking, because if we tried this out, if we put an 8p here and a p here, we might have spinned our wheels for a while trying out all of these. None of them work, because we had to actually go this route, 4p times 2p. But we did it, folks. That's another one down. Any questions on getting through this one? Okay, one last one, and we'll call it a day for today. 72x squared minus 264xy plus 242y squared. This one looks really problematic. In view of what we did above with this trial and error, and the numbers were a little bit more tame, this one looks spectacularly nasty. But never forget the step 1. There's a greatest common factor here, because all of these terms are even. We can factor out a 2 at least. 72 divided by 2 is a 36, but that's a perfect square. And 242 divided by 2 is 121. But 121 is nice as well. 11 squared is 121. So if we only factor out the 2 here, we get another perfect square. So here's our first step on this one. Factoring out a 2 is going to leave behind 36x squared. 2 divided by here is going to be negative 132xy. And factoring out 2 here leaves positive 121 y squared. So our hopes of hopes that this is possibly a perfect square trinomial. I say possibly because if that number is wrong, if it's something different, it could throw out the whole pattern. So we do have to check out if it's going to actually work for these last ones. So if it were to work, here's how we should try it out. 36x squared, the most natural thing to try on this one should be 6x times 6x, using the perfect square, 6 times 6, giving the 36. So let's place them down and just hope for the best on this one. Next thing, positive here, minus here says we have to use 2 negative signs. 121 y squared, we could try out as 11y times 11y. So let's go 11y here, 11y here. And the check always looks the same on these. We multiply here to here, that's going to be negative 66xy. We're going for negative 132 of them, but multiply it again, we get the same thing twice. Negative 66xy. Adding 66 to itself is carry the 132. So that actually works out. It hits the middle term. So that tells us this whole thing, which looks nasty, it reveals its true form once you factor out the greatest common factor. And now in this format, we can easier write it as 2 times 6x minus 11y to power 2. So that seals the deal. That's how this one factors. That's our full tour then on our factorization techniques. When we come back on our Thursday's class, we'll look into how to apply these things. I mean, that's good news in a way. It means we're going to still practice how factoring works. Even in the very next section, factoring is going to be used all over the place in this course, and this is really just our first look at it. We'll be applying these to solving equations in the next section. Well, any last questions at all, folks, before we call it a night? Okay, well, have a great night. Looks like we'll end class today just a few minutes early. 3 minutes is definitely not enough time to start a new section. So we'll be in section 6.5 on Thursday's class. Take care, folks. Thanks.